Thanks a lot for the kind introduction. So I hope you can see my slides and also hear me. At least Zoom tells me so.
Yep, you can.
Okay, thanks. So I'm talking about relative binding free energies, and especially with the methods RE-EDS. And this is going into the direction of multi-state methods for free energy calculations. So quickly, here is the obligatory thermodynamic cycle that we have already seen also yesterday multiple times. And if we are interested in relative binding free energies, we are interested in this red arrow in order, for example, to compare different drug compounds in how well they would perform on inhibiting, for example, a certain enzyme. Also yesterday, we already heard multiple times that there are different ways how we could basically retrieve information from this red arrow. And one way is we could do an absolute binding free energy approach for both of our molecules and then use them to get the relative binding free energy. This is possible and is shown multiple times in the literature that it really works, but sometimes it can be very complicated and it's not that easy to get converged results for. So an alternative approach would be the alchemical free energy difference calculation, which you can also use to get the relative binding free energy. And this tends to be faster usually. But in reality, we're not looking only at these two molecules. In reality, we're looking at a set of molecules. And so we are also interested, of course, in the ranking of multiple compounds to each other. And so here, for example, now we have 5 ligands in 2 different environments. So one environment is water and the other environment is the protein. And now we want to know which of these is the one that is binding best to our protein. The graph that you see in front of you is one way on how you could do these calculations in order to be able to compare all these different ligands. But it's of course not the only way. We also had yesterday the star map approach or something like this you could also use, of course. And this already leads to a problem. Because now if we have, of course, first of all, we want to optimize our computational performance usage. So this means that we only want to calculate a minimal amount of edges because these are the very expensive things we are calculating, like with TI or FEP. So in order to do that, we want to find a graph that is efficient on this and still connects everyone to everyone somehow. But what happens if this compound A and compound B are leading to a transition that is not easy to facilitate because there might be a sampling barrier or something like that? What happens if it might be more beneficial if a path via the compound C here to compound B would be more beneficial to the whole approach? This is something you cannot always see beforehand. And I think that EDS, enveloping distribution sampling, which was developed by Christ, is an interesting approach in order of solving this. So what you do here, instead of sampling really the direct edges, you generate reference state that can explore the whole graph of one environment. So this would mean here the green cycle is combining all the water ligands together into one system. And here you combine all the ligands together in one protein system. This is done in our approach in a dual topology approach where we have only the ligands present there on a dual topology, and the environment, of course, is always the same. And how do we build this reference state? So this reference state potential function is built like this. Here on the right, you see 3 ligands for our system. They are represented here as harmonic oscillators with their potential function. And the reference state is an exponential coupling of these different end states. So what it basically represents is here in green, and this translates to the green circles you've seen before. And here you can also, I will talk in a second about these 2 colored parameters, which you can use then to tweak our potential here. If we want to sample this potential now, what we do is we scale the forces by the contribution of a state to the reference state. So this translates like if we would start here now with our simulation, the blue state is mainly contributing to the sampling of our system. and such that we can get a physical, meaningful representation of our blue state. And maybe at some time point, which we didn't do here in this beautiful simulation, we could cross the barrier and now switch to another state here, which didn't happen. The blue one here is, as I said before, the one that is defining the environment as well, and is sampled in a physical, meaningful way. This also leads to a state or a way of sampling for this blue state as dominating state. Because as the state here is contributing the most to the reference potential, it also is the one that is kind of leading the sampling. And the second term, which we call a second way of sampling, is occurrence sampling. That's also something I want to introduce to you. This is something that if the potential energy is very close to the dominating state, then it could be that multiple states are contributing to the sampling at the same time point. This could be due to phase space overlap or over smoothing of our potential. I will come in a second to that. So now I promised you to talk about the two parameters. So first parameter is the smoothing parameter, the S parameter. This is used to decrease the barriers between the different end states and such that we can facilitate transitions between different end states. This can also be overdone in a sense, and this leads to undersampling, which is something I will talk about again in a second. The other parameter is the energy offset. The energy offset is used to align the different end states relatively in the reference state to each other, such that if we can make the transitions between the different end states, we can have an equal weighting of sampling in these different end state regions. The final ingredients of our approach is then the calculation of the free energies after the sampling. And this is done via the reference state. So what we do is we can get all the different free energies from one simulation, so in one environment, for all the different states that are present there via this reference state. And this is just a linkage of two Swansig approaches that we are using here. And now it's RE-EDS, so there's a second part to it, and this is the replica exchange part that is tremendously boosting our sampling. So what we are using here is not a single S value like before, but we are using a distribution of S values such that we can build up a replica exchange graph and exchange the replicas in a Hamiltonian replica exchange-like fashion. So here on the left, you see different S values that lead to differently smoothed potential energy landscapes, which we can sample at the same time point. And starting, for example, here in blue, we could start sampling here. And after some time point, we could exchange our coordinates and do that multiple times. And this might lead to a path from this state blue via lower, so stronger smoothed replicas to, again, then less smoothed replicas, such that we can see a second physical interesting state. And we only use this physical region up here to calculate our free energy in the end. The rest is only used as a pathway. And I mentioned before, the top here is physical. Then we have this so-called transition region. And here's the undersampling region, again, that I mentioned before. We also have that present in our approach. Physical, I think I explained already, but the undersampling region, how can you imagine undersampling in general? It's like every state is kind of contributing to our reference state at the same time point, such that the environment also sees all the different ligands at the same time here. This allows us, of course, to facilitate so transitions to each of the different end states, but is of course not necessarily required. And after this introduction into the methodology, I would like to show you the system that we used now in this current approach. This is the human checkpoint kinase 1, which was, so the system was designed by Wang, by Schrödinger for an FEP Plus benchmark paper with a cycle closure approach. And what you see here, the interesting part of this set basically is that you have these different, quite large differences in our set that are basically typed as scaffold hopping-like transformations, such that you can open the ring here to a very complex entropic dihedral sampling, what you need here, or you have an increasement in your cycles. And this system we use now to do our simulations, and I will show you the workflow that we now use to really define all the different parameters that I introduced you to before, and also how we build up our final production run. So in our workflow that is automatized, we're using now as a first step, first of all, we have input parameters where we use initial guesses, a log distributed S range that is very large. And we set these energy offsets to 0 as an initial start. And of course, we have our system. In the first step now, we try to limit the S distribution to a reasonable range. This means basically that we don't gain much information via this undersampling. So it's of interest to cut it efficiently at some time point. And so we do super, super short simulations where we detect when our systems start to fall in this so-called undersampling regime. So this is when here, what you see in yellow, because blue is showing us occurrence sampling at the same time point. And this very blue down here shows that all the different states are contributing to the reference state sampling at the same time point. This is what we determine as undersampling. And in this first step, as I said before, we detect this yellow limit and then add 2 replicas to it to get a lower bound of our replica distribution. In the second step, what we do is we use EDS runs to force our system into different end states. So this is the second preparational phase where we generate all the different coordinate sets for each of the different end states. So what you see here now. This is done by setting the energy offsets correctly so that we overweight basically the different desired end states. And we can also show this from very short simulations that here in colored are the potential energy distribution functions that are sampled during this approach for the desired ligand. And in black, we have a single state MD simulation, which shows that we are clearly in a similar energy distribution compared to the single state MD. And this is true for water and also for the complex. And these coordinates we can use then to seed our replica exchange approach. So classically, we started with one starting state. And so we only started here in one area of our phase space and started to explore everything. And now we added to this the starting state mixing approach such that we can use the end states that we generated before and use them alternating through our replica exchange graph and enhance our sampling even further. This idea is not entirely new. It was already used by Graf in 2016 and Hahn in 2020, for example, to boost 2-state systems. And we do it now with a multi-state system here. In the next step now, after we did this initial exploration, what we do is we estimate the parameters for our EDS approach. Initially, we estimate the energy offsets from an undersampling regime such that we can better weight the sampling of our approach. And this is basically what you see here, and kind of what you can detect also if you fall into an undersampling situation, the results of our different replicas converge to a certain range, which is actually quite nice to see. In the last optimization phase now, what we do or need to do is to optimize our S distribution that we are using, because it's actually quite typical for replica exchange approaches that you might have so-called bottleneck regions in your replica graph. And this translates to regions where you have a low exchange frequency. So like you basically would cut your replica graph like here where the red line is. And we can also see this. This is only the first 250 trials, but you see here, for example, there's a very low. So in this first 250 trials, you have actually no exchange that is done via this bottleneck. So this is a problem. And we use an approach that was developed by Siedler that is called the end-state linear round-trip optimization algorithm. So what this approach does, it detects the exchange frequencies of the different replica positions and identifies bottlenecks, as I mentioned before, and adds linearly replicas to this. So we add 4 replica per iteration, and you do that multiple times and then assess your optimization approach. And here you see one example for the SSM approach in the complex. So in the beginning, we have a very low number of round trips. So this here is the total number of round trips during our optimization run. in the beginning very low, and then we have a very quick increasing first step, and this is actually already quite nice to see, and then we can optimize this number. This is the round trip time. The round trip time is basically defined by from going from top to bottom to top. And the average round trip time, of course, should decrease. And what you see here also after 2-3 steps, it's already a lot decreased. And we decide to stop this process of optimization after, I think, 5, I know that after 5 iterations, because here now the optimization improvement is super low. That's such that we consider this approach converged. And you also see that what the algorithm does, it adds the replicas, of course, into the region where you would expect this bottleneck here lies. And you see that from iteration to iteration, this is getting more replicas stuffed in here. And it's also then leading to better exchanges. And here you see the final product of our optimization. So this is step 5. Here you see that all the bottlenecks that were visible before is now not easy to spot anymore. And after this last final optimization run, we can step to our production. So here again, you see the ligands. This is a 4 nanosecond production run. And what we see is in principle that many values here look quite nice. In blue, you see the SSM approach. So this is the starting state mixing approach where we did these different end state mixings. And in green, you see the approach without the mixing. It's actually quite interesting to spot immediately that here, this 1L19 ligand is actually having quite high deviations. So this seems to be not very well sampled in our approach because the deviations are very large. If we now start to compare the correlations also of the two approaches, here again, you see that our ligands are this 19 ligand is not very well sampled, but for all the others that are sampled, actually the accuracy seems to be in range of the 1 kcal, which is the grayish line here. I want just to point out one thing. I calculated all the possible edges of the state graph, which you can actually have in this case. So this is why these data looks a bit mirrored. And now we can also compare it, of course, our results to the results by Wang and also by Jespers, who has the QLIC-FAB approach. And both papers are, of course, published. Here, the accuracy in comparison to our RE-EDS approach, if we're not talking about the 1SS approach, because here we have, of course, due to our outliers, a not very well or nice accuracy, but I would argue that the accuracy of our SSM approach is comparable with FEP Plus and QLIC-FAB. The ranking correlation, I think this is a very interesting approach. Here we have to say, to be fair, that we needed to calculate some edges via present edges in the state graph, such that the correlation here is a bit lower now. And if we take the all the edges that we inherently get from our approach, we actually get a quite high correlation, which is, I think, a very interesting fact to see for our approach. And for the last criterion that I want to compare here is the production time. Here, what I display is the total number of simulation nanoseconds. So in the FEP Plus, of course, I collapsed all the different lambda windows into one big number. So what you see is here we have 650 nanoseconds. So this is the approach that required it, at least in the publication, the most simulation time. And the QLIC-FAB one is the fastest one with very impressive 80 nanoseconds, and we are somewhere here in the middle. This is kind of the comparison of all these different methods. I think that RE-EDS has an interesting or side on the correlation. And last but not least, regarding the simulation time, we have these 308 nanoseconds, but I think actually we could dramatically reduce the number of required production simulation time if we, for example, implement detection for convergence in our approach, because what you see here now is the convergence of the free energies. Each vertical line is showing you the estimated convergence. I think the difference is only 0.25 kJ per mole. If value converged to that, then we consider it as converged. And it's actually quite clear that we don't need these 4 nanoseconds for our approach, but we could actually already use maybe 1 to 1.5 nanoseconds. And this would, of course, dramatically cut the cost. And with this, I come to conclusions. So I presented you an automatized workflow that is able to do these complex core hopping-like transformations in a multi-state method, which is actually, I think, a very interesting aspect of this method. If you're interested in the code, you can check out the GitHub from the Replica lab. There we have all the different repositories that were required for the project and the talk. And also as an outlook, I think it's very interesting for us to apply our current scheme to more diverse targets and to other systems. It would be very interesting, of course, to also optimize the performance for the optimization and the production run, what I showed you. And also it would be very nice to have an automatic scheme for the restraint placement of our dual topology approach, where we are actually working on. This is the restraint maker. And with that, I want to thank Seraina Rinnecker for giving me the opportunity to work on this beautiful project, and the whole group and the people that helped me and collaborated with me on the project. And I want to thank you for your attention. I'm happy to take your questions.
Thank you very much, Benjamin. Very nice talk. So yeah, we've got some time for a few questions. So we've got a few in already. So the first one is from Julian Michel. He says, Benjamin, very nice explanation of RE-EDS approach. What is the maximum number of compounds that can be reasonably handled with the present parameters tuning approach? Would it be beneficial to keep the coordinates of the molecules aligned on a common core throughout the simulation?
So the maximum number of ligands that we used so far were 9 ligands, which was in the Siedler publications. You can see it there. And of course, this is something where we are playing around a lot now to see how far we can go with this method and how many ligands we can combine. And if I understood the second question correct, it was about the common core of coordinates.
Would it be beneficial to keep the coordinates of the molecules aligned on a common core throughout the simulation?
Yes, that's kind of what we do. So if I go back quickly, sorry. Exactly. So what you see here, they share a common core here on this blue part, and we use this to restrain the ligands to each other. So in our dual topology approach, we have a set of restraints, which is keeping the cores of these common shared structure parts together. So yes, this is very beneficial also in the sampling manner.
Great, thanks. So we have another question from Aber Leffler. Benjamin, did you test using R group changes as well?
Sorry, that?
Did you test using R group changes as well?
I think I didn't understand it acoustically, probably. Maybe that's something I can look up later.
Okay, sure. Yeah, we'll move on to another question. So the next one's from Emilio. Nice talk. Can you please go over the definition of the degrees of freedom again? Are all system coordinates replicated or only the ligand coordinates?
Okay, yeah, of course. So that's exactly the slide again. So here, what you see already in this small zoom in, what we do is we only replicate the coordinates of the ligands. So we have these ligands here, like I already said, we also make them overlay. They are perturbed to each other, so they don't see each other. They only see the environment and only contribute to the sampling actively, depending on their potential energy. But the protein itself, we only have once in our simulation box. That's very important because, of course, you don't waste too much simulation time. And it's the same with the water boxes, basically. So the environment around our ligands is only there once, usually.
Great, thanks. I think we've got time for one more quick question. So Martin Reinhardt says, very nice work and method. what kind of software do you use to avoid singularities for vanishing particles?
In this case, we not really have vanishing particles, I would argue. So due to the momentum scaling, I think we always have so we also don't need soft bonded core terms, for example, because due to the scaling, we avoid singularities usually. So we don't have that in the approach normal. But maybe we can also discuss this later.
Okay, great, thanks. I think in the interest of time, we should probably move on now, but thanks again, Benjamin. You've got a few more questions in the Q&A box if you wouldn't mind answering those once you've had time to relax a bit. So
sure.
yeah, so thanks again. So our next speaker